and where I show you some application examples, and they're quite diverse. So I work in a lot of different areas, which I think is really nice. But this is also a sign that all these methods can be used for a lot of different applications and use cases. Okay, and I will start with whale monitoring. So as you might know, hopefully, so the whale populations are threatened by commercial whaling, ocean warming, and competition for food. And so it's important to monitor whales and their spatio-temporal migration. And this is done by looking on many, many photos, and they're mainly taken by tourists, and specific whales are identified by these photos. And this is currently still done manually, or mainly manually, and experts look primarily at the corners, here at the corners of the fluke, the shape or special features such as scars. And to find an automatic solution for this task, the CACA challenge was initiated a few years ago, in which several thousands of whales are to be assigned with only a few pictures. So we had several thousands of classes, and each class only had a few images, sometimes only 3 images for training. And it was not surprising that the 3 winning solutions were neural networks, and we took one of these neural networks to analyze it more deeply. It was actually the second winning solution, because the first one was not so easy to handle, but the second winning solution was also okay, and we had a deeper look at it. And the research questions we can formulate here are actually, why does the network identify images as the same whale or as different whales? Or is a whale expert looking at the same area in the image as the network? And the reason why we want to find this out is because, first of all, it's very interesting, because a few years ago, I was approached by a whale expert, and we had a chat, and then we were actually came up with these questions. But also from a machine learning perspective, if the network behaves similar then to a whale expert, we can exploit the expert knowledge much, much better. For example, we know that scars can change over time, so it might not be a good or not a relevant feature for identification. And so for our analysis, we use 2 interpretation tools. One is occlusion sensitivity maps, and the other one is GradCam. So GradCam is gradient-based class activation maps. And here I will explain class activation maps and then the extension also to GradCam. And I want to show you the principle behind these 2 in the next few slides. But first, I want to, so the first method is occlusion sensitivity maps. I'm a big fan of occlusion sensitivity maps because they have really good behavior. And for most of the application I used them so far, we got good results. Yeah. And so what do occlusion sensitivity maps actually, what do they do? They evaluate the sensitivity of the trained model to occlusions. So it's a post hoc method, and you see how the output changes when you change the input. And it actually analyzes the difference between the original score and the score after applying an occlusion. So what you do here, you have an input image. Important thing, you have an already trained model. So this is done post hoc. So you have a trained model. For example, here's some occlusion, not occlusion, convolutions, convolutional blocks. And in the end, you have a decision layer for a specific whale ID. And then you have an input image, which you want to analyze. And what you do is you define such a patch here, and you slide the patch over the image and occlude specific parts in the image. And so you have the score before the occlusion and the score after the occlusion. And the occlusion sensitivity is nothing else than the difference. So very easy. And so what is the result? This is such a heat map with a little bit different colors. So in this case, we illustrated it in green and in purple. So green values mean that the score decreases after you applied the occlusion. So regions are an indicator for a specific whale. So if you cover it up and the score decreases, it means, oh, that was important. So it was bad that it's covered up. And then there are purple values, for example, here in the background a few. And here it means the score increases. And this is a little bit tricky to, to actually came up what it means, because it depends on the loss function. But what it means is the regions are an indicator for other whales or just not the specific whale. So in the end, it actually means that it would be better to have them covered up. But the important thing is here the green part. And so what are the advantages and disadvantages? First of all, it's simple and versatile. I could explain, hopefully I could explain occlusion sensitivity maps to you in one slide. So it's a very simple approach, and it's versatile because it can be used in the input image, but it can also be used within the network. You can use it with features, with time steps, with everything else. So the principle behind is something you can use for a lot of different approaches, so depending on what you want to analyze. It's model agnostic. That means you don't need access to the model, and also you can apply to all kinds of models. Can be neural network, random forest, whatever you want to analyze. However, the definition of the patch is challenging. So first of all, the patch is agnostic, so semantic segments which can differ in size. For the whale fluke, imagine you have the shape, or you have some specific scars and so on. But these are different in size. So it's how to choose the patch, the bigger, smaller one. What you normally do is you choose different sizes and then you combine them, or you have several outputs in the end. Then also every occlusion is a signal. So you cannot really cover up something, so it's not missing. And so if you use, for example, a patch which has a single value like 0, it's always a patch, it's always a pattern. Or you can use noise, which is a little bit better, or you can use a Gaussian kernel, so you blur the current appearance there. So this is also a good decision to do. And there's a distribution shift. So the patch might be out of distribution. So every time you learn a model, you have training data, and they represent a specific distribution. And the changed input with the occlusion might be no longer in the data distribution we trained the model on. So we generally assume that the model will be evaluated on data coming from the same distribution as the training sample. So if this is not the case, so if you change some kind of pixels, then the model output might be wrong. So be careful if you change the image too much. It might be just not something the model has ever seen before, and then you might get the wrong result. And also, it's computationally expensive because you have, again, this sliding window approach, and you need to evaluate it. And then you can even go one step further and analyze not only single heat maps, but also the whole decision process by analyzing all heat maps together. So this is actually an analysis technique on top. And this can be done by performing clustering, and specifically spectral clustering of the occlusion sensitivity maps. And the goal is to identify patterns in the decision process of the model. So it's not anymore about single prediction, but the whole decision process. And here is a teaser. I will go more into detail in the next slide. These are some clusters, which we could find in the data, and you can learn something about the cluster, or you can see something in it. And you can already see that the cluster highlight and separate different features. And so the heat maps look similar, and they will tell you something. But how did we perform this? So I don't know if you are familiar with spectral clustering, but I will give a brief introduction what it is. So this Also, not connected to explainable machine learning, spectral clustering is also really cool. So you can also use it without in another context. So first of all, what we did is you extract the heat maps from samples of interest. It means a test data set. Then you vectorize the heat maps, unify the size, and then you reduce the dimensionality, for example, with PCA. It means you have these vectorized images, and then you delete all the dimensions where you have zero variance or close to zero variance. And then you perform spectral clustering. I will tell on the next slide what it is. And then you perform an eigengap analysis, because spectral clustering depends on eigenvalue decomposition. And the eigengap analysis is that you actually have an indicator how many clusters you should get from the data, or when clusters are not really distinguishable from another cluster anymore. So spectral clustering, what is it? Spectral clustering clusters the data based on their similarities to each other. So it's not that you take the input immediately, the RGB values, but you take similarities between all the test data samples. And for this, we need a similarity matrix W. And this matrix W can, for example, be derived by using a radius around each point or a k-nearest neighbor approach. So here illustrated are single data points. Of course, we are in a high dimensional space, but here I illustrated it in 2D. So these data points are these vectorized heat maps. And then you have, for example, here 1 point, and then you have a specific radius, and then you determine which of the other heat maps are similar. That means they have a close Euclidean distance. And then you have such a matrix. This matrix has the size of number of test samples times number of test samples, and then you feed in all the neighbors. So this is the similarity matrix. You can also do this with the k-nearest neighbor approach, but yeah, that's just another possibility. For the k-nearest neighbor approach, we additionally need to make the matrix symmetric. For example, by transposing it and taking the maximum. So you need symmetric matrix. Okay, so now we have the similarity matrix, but then we need another matrix, is D, which is a diagonal matrix, which is derived by summing W over all rows. So you have the rows, and then you sum it up, and then you have a vector, and out of the vector you make a diagonal matrix. And if you if you subtract the diagonal matrix and the W matrix, you get the so-called Laplacian matrix. Maybe you already heard about it somewhere. Laplacian matrix is used in also in other areas of machine learning. But this is actually a matrix where you then perform eigenvalue decomposition on it. So, and then you cluster the eigenvectors. If it's too complicated, it doesn't matter. What is important is that this clustering technique helps you to, if your data has some patterns, but they are very complex on complex manifolds, it gives you a good clustering because it's based on the similarities, not on the original input data. So it will help you with complex structures to cluster them. Yes. So now we have these eigenvectors and the eigenvalues, and so the eigenvectors are clustered. So we get the cluster assignments, and due to the eigenvalues, we can analyze this gap and say, okay, here when you have a jump, or when it's not changing anymore, it's it tells you, okay, it's not. Or if you have low eigenvalues, you just say, I don't care. It's until then I have the number of clusters and I don't need more clusters. In our case, we had 29 clusters. And so here you can see, for example, one cluster. on the left. And here the whole, so when we look at this, it seems that the heat maps indicate that the whole fluke is important because it covers the whole fluke, which could be an indicator for the shape. The second cluster is here the pigmentation near the fluke tips are important here. And on the right, this is a cluster where we cannot really see a pattern. So this, it seems that there are also some leftover clusters where, yeah, no distinct patterns are included. Okay, I forgot to say what we specifically did is that we computed for each test image the heat map which belongs to the highest score. So this might be a correct decision or not. So we took the decision and the highest score, and then we had a look. Okay, what it might be wrong or not. We independent of this, we took this for clustering, and then something we went even further because it's now interesting to have these clusters, but what can we actually learn from it? So what we did is we related the detection rate to the heat maps. That means we computed how many of the heat maps belong to the correct decision in each cluster. And we were not too strict, so we used the top 5 predictions. What does it mean? So this is a thing from machine learning, and when you use it for identification, that you not use the top 1 prediction, but top 5. Top 1 prediction means that the assignment with the highest score was also the correct assignment. Top 2 means, top 2 prediction means that the second highest score was the correct whale ID, and so on. And we count it as correct if it's within the top 5 predictions. So this is something which is very often done also for benchmark challenges, that you have a top 1 prediction score, and top 3 and top 5. And this is compared. And here what we did is we plotted the cluster number versus the number of correct assignment, and the clusters are sorted. So it's nicer to see. The clusters are sorted by the number of correctly assigned whales. And if you, for example, here have such a heat map in cluster 1, you can see that 90% of the heat maps belong to top 1 prediction. So that means the assignment with the highest score was also the correct one. And if you have such a heat map, it can increase the trust in the result. So if you see you have such a heat map, obviously the network found good patterns, so it's obviously reliable. And for many clusters, you have wrong predictions. That means the heat maps belong to test images which were not classified correctly. Overall, it turned out that some types of heat maps are associated with very high detection rates and some are not. And also that some clusters contain almost only correctly assigned whales. So that means if the network is looking at certain characteristics of the fluke, then it can be said how reliable the network can detect this whale. And you already see when I talk, it's connected to uncertainty. So you can see it as an alternative uncertainty measure beside the actual score of the network. So what are our insights? I already mentioned a few of them. So some clusters can be assigned to high identification rates. So we found out specific characteristics are good for identification. For example, the shape of the fluke, when you had the whole fluke covered, that was really good. Versus the time variable scars, that was also confirmed our prior knowledge. And we could also confirm that the network looks at the right feature. So there was no Clever-Hans effect. That means no right decision for the wrong reasons. And I already talked to Hannah in the break, and that it's not so easy to design a network on our own and find data to actually get the Clever-Hans effect, so to provoke it. Yeah, but this is something we are planning for. That would be cool. Maybe it's possible with the whales by just having one whale and there's always a mountain in the back or so, something like this. But the good thing is for the user, it would be possible to have a real-time evaluation of a photograph. I mean, this is nothing we did already, but imagine the following: you take a picture as a tourist and you upload it to a database. Some tourists like to do this. They photograph flukes and they upload it to a database, and then it's evaluated what whale it is. But imagine you would get a feedback which tells you this might not be a good picture. It's not so good for identification. We cannot rely on the decision. Try to get another picture or something like this. That would be actually really nice. So besides occlusion sensitivity maps, we also used gradient-based class activation maps, so which is based on class activation maps. So first I will explain what class activation maps are, and then the extensions to GradChem. And so class activation maps are specifically designed for convolutional neural networks. And you already see a difference. So occlusion sensitivity map could be used for any algorithm, and this is specifically now for convolutional neural networks. And the goal is to indicate the discriminative regions used by the CNN for classification. So let's have a closer look in how it works. So when we look at the simple convolutional neural network for detection, then we have convolutional blocks here. And the last convolutional layer, this one here, is flattened. As I said before, this is just by vectorizing it. Then we have some fully connected layer, because it's a very high dimensional flattening, and then we need to reduce this to get to our final decision. So normally what you do is you have some fully connected layer to get some non-linearities for the decision. And you can have a sigmoid or softmax for final decision. Also, I forgot to mention the first part, difference between softmax and sigmoid. In this case, for the whales, we used as a final decision sigmoid. So that means we get a value between 0 and 1, but not all whale classes sum up to 1. This is good because if we have a sigmoid value, which is low everywhere, we can see that this test whale might not be in the database. So there's an additional class, which when the test image whale cannot be related to any of these. If you would use softmax, all the final scores would add up to 1. So you would have a lot of high scores, or you would have one higher score, something like this. So it would not tell you that this way it might not be in the database. So for such cases, really good to use the sigmoid. When we want to compute class activation maps, so keep this in mind here, we replace the fully connected layer, which was here, with the so-called global average pooling layer, which you can also find in a lot of neural networks nowadays. Global average pooling averages the activations of each activation map and concatenates these averages and outputs them as a vector. So here you can see I colored them, all the single activation maps A, K. And you just take the average to get one value, and this is concatenated. So this is very easy principle. This is global average pooling. And then a weighted sum of this vector is fed to the final decision layer, for example, softmax or sigmoid. So all of these values which get out of the global average pooling are connected to the final decisions, and they are connected with a weight. And this is actually the weight. So C is the index for the class, and K is the index of the global average pooled values. Okay, and these CAM class activation maps is in the end very simple. When you multiply these weights in the final layer with these activation maps, and this is okay. This is for GradCamp, but it would look at this would look similar. This is specific for one class. Yeah.
And these weights you have to learn as well, or they kind of determined somehow else?
Yes. So they are not. You mean these W?
WCK, yeah.
Mm-hmm. Yes, this is learned. So so this method is specifically for, you need to implement it into a neural network. So it's not that you can apply it post hoc, but it's implemented and then it's learned with them.
Did you really learn kind of two things at the same time? So kind of identifying it, and also you put them like branch somewhere. And
yes.
You also
yeah. So it's actually what is mostly done. You have these anyway, such a flattening and fully connected for the decision part in the end, and you just replace it. And so you replace it with some architecture part, which can be immediately used to get such a map.
Everything up to the end of AK is done once, and then you go.
Yeah. The bad thing is you only can analyze the last convolutional layer, so it actually needs to be here. So it's very restricted in how you can actually use this. And that's why that's actually the reason why the gradient weighted class activation maps were developed, which is an extension, and which weights the activation maps based on gradients. So now we analyze the gradients. It's more versatile, and it produces visual explanations, or first interpretation, then explanation for any arbitrary convolutional neural network. So again, we look at the network with multiple layers, and we want to analyze the last convolutional layer because this is advised to do so, but you could also look at other convolutional layers. That was not the case before. So there's this is how you compute it, and I want to go with you through each part of it, because I think it's always like this. You get an interpretation method. You will see it also later with the Shapley values. Then you get such an equation, and the first thing you think is, okay, why, how? But if you go through it, it gets clear. So this is what I want to do with you now. Yeah, this is where we start. So step one here. First of all, you forward propagate the input image through the CNN, and you obtain the raw score for the class of interest before applying softmax or sigmoid. And then you set all other scores to 0. Raw score means that it's the score before you apply sigmoid or softmax. So this is the logic. So you don't do it afterwards, but before. And because you only want to know something about one class, you set all other scores to 0. And yeah, so this is here the YC, this is the score. In step 2, you backpropagate the gradient of the raw score of a specific whale ID to the convolutional layer you're interested in. So this is what I mentioned already before with the backpropagation. So what you do is you have a forward. When you have this network, you can also backpropagate and see what the gradients do. And this is actually this part here. So yeah. And then this is something you already know. This is global average pooling. That means the gradients are averaged across the activation maps. So activation maps were the A, I, and J are the refer to the position in the activation map. So you sum over all of them. And Z is the number of positions. And then, this is also something to mention. If you are not really, or if you always search for an intuition about something like I do, so this can be interpreted as the importance of each activation map for the target class. Overall activation maps, we have K of these activation maps, and they are weighted by their importance this year. So it's very similar to the concept what I showed you before with the class activation maps, but here you use the gradients and in the end, it gets more, yeah. And the last part, this is actually a mistake. So this is here, this one needs to be highlighted. Now, ReLU is applied to consider only the values with a positive influence. The reason is that GradCam removes all negatives or negative with the argument that we are only interested in paths that contribute to the selected class C and not to other classes. So we only want to have the positive influence, the positive impact. And for visualization, you scale the values of this final heat map you get. The same size as the image, and you scale it between 0 and 1. And this whole procedure, they're actually really nice toolboxes which can be used. And this procedure is recommended for the last convolutional layer, but you're not restricted to it. So you can have a look into. There might be others, but we were not selecting family. But yes, we have findings. We work together with our way is our way is first we also look at similar more than they look at more than one. That was actually what we also we try to find several ones, normally 3 to 4. He said, but we were not able to. Yes.
So in these images, the patch is always on the right side, right? Did you also try to augment the image and
yes,
and could it identify the different side also?
Yeah. Okay. We had actually good. I already forgot. We had a really nice finding because sometimes the network was looking at the middle notch, and it was never on the notch. It was always a little bit under it, and we were thinking, why? So why does it not go in the middle? And so we rotated the images, and then it always went towards in the middle to the fluke. So we think it's maybe because the pattern found by the neural network is exactly that it's it will not be influenced by the water behind or something like this. That's what we think would happen. But so we tried also to, yes. Yeah.
Do these heat maps correlate with the position of Cheeseman when he chooses which.
Yeah. Yeah, we have a newer publication where we tested another approach. I did not show it here, and there we gave him images, and then he needed to sign why he thinks it's the same way or not the same way, and then we compared it, and mostly it was one of the features he also indicated, but sometimes it's really hard to compare because he would never really say the shape of the fluke is important. He would maybe say because of the curvature or like so this is something where clearly the network and the expert
but he has some sort of ranking in this decision making too.
Not really a ranking, but he would say he looks for 3 distinct patterns, the most important ones without ranking, and then a few more which has a lower rank. Yeah. Yeah, Hannah.
I wonder whether it might be dangerous in some cases to apply data augmentation here, because if you think you flip the image, then the notch would be on the other side of the fluke. But as a whale expert, so you recognize that this is a whale because on the right side it has a notch, and it is definitely not the same whale if it's on the left side. But I guess that the model would make a prediction that this is the same individual, wouldn't it? Or did you try things like that?
Yes, we tried things like that, but we actually thought about it before applying augmentation. So we just did the upside down flipping, or that actually it was already included in the training and treated as a different whale. So this, for some reason, for all winning solution, that worked very well, that you produce some more whales, which is, I don't know why, but it worked very well. But we only did this augmentation or some changes in the image to see, to understand the heat maps in a better way. So it's not that we really performed augmentations which would change or which would lead to wrong results. It was just because of the notch that we rotated it because we want to see why it's exactly located there. Or what we also did is we changed the background a little bit and changed how, if the result would be influenced, if the heat map looks different, if we only see the fluke without the background, something like this, which is interesting.
And so you have kind of more whales in the publication. So if you look at different whales and how the maps change.
I don't know. I have more results definitely, but I don't think that we have it somewhere. Yeah, I don't know. I'm not sure. In our new publication, which was from this year, there we have definitely more whales, and also the comparison to the whale expert. But that's a different approach. So we use a landmark-based approach where we search for landmarks in the image, and then the like key points when you register images. And so that was different. And we wanted to have a look if also a landmark-based approach can be used for interpretability and explainability. Yeah, but if you're interested, I have a lot more heat maps and whales. It's yeah. Good. Then in the second part, it's actually second part. I want to have a look in the ozone value estimation, which is a nice contrast because so far I was talking about images and heat maps, but now what is when you have single values and you want to analyze the single values. So I want to talk about Shapley values, and Shapley values, everything what I say now is also applicable to images, but I could not show the first results yet because yeah, we are working on it. But it's actually all what that tells also can be applied to images. And so yeah, have a look. Let's have a look at the mapping of tropospheric ozone. So ozone is a toxic greenhouse gas with highly variable spatial distribution, and highly variable means it's not so easy to map it. And so far, the relation between this geospatial data and ozone metrics is not well understood. And fortunately, there are some research groups which develop data set for it. So Scarlett is in one of these research groups, so that we can have a deeper look into it and develop models which can relate this geospatial data with ozone values. So one research question in the context of explainable machine learning is if we learn a model that maps these geospatial data to ozone values, what are the most important features? So this is actually a question which is not new, but when we use for example, neural networks or some other or due to the development of neural networks, a lot of new methods popped up in the last years. So we tried a new method called Shapley values. Here I can recommend to have a look. So this is the data set if you also want to try it out. This one, the AQ bench data set. Yes, and as I said, for this we can use Shapley values. They are a local interpretation of the output by means of the input. That means it's a post hoc method and it's model agnostic. That means these can be used for all kinds of models. And it's theoretical basis from game theory. And what I realized in the last few years, there are a lot of algorithms which are based on game theory in the area of deep neural networks. For example, also this generative adversarial networks, which can generate new images from noise or from other inputs. They're also the optimization is built on game theory. So the question is now, how much has each feature value contributed to the prediction compared to the average prediction? So it's I know it's not so easy to understand the Shapley values and what they actually tell, and it's very often misinterpreted. That's why I would repeat it in the next slide very often. So it's the question is which feature is responsible for the change. So when you have a single vector, a single sample with feature values, why does it predict something else than the average? This is the question which can be answered with the Shapley values. So let's have a look what Shapley values are, and let's start with the game theory. So here we have 4 players, and these players are in a coalition. A coalition is an alliance for combined action, so they play together. And they play a game, and from the game they have an overall payout. And now the question is, what is the contribution of each single player to the overall payout? So you want to have an assignment of a payout to each player based on the contribution. And so now you might ask, okay, that's nice, but we are actually doing data science. So how can we now transfer it to data science? And this can be done in the following way. So we have given a set of features, x1, x2, x3, x4. This is a set of features with given values. So this is a sample. And this is nothing else than the players in the coalition. So they work together for the prediction. Then you have a prediction task for a single instance. This is the game. And then you have the output, which is the overall payout. So this is the prediction value in the end. And the question stays the same. So what is the contribution of each single feature to the overall payout? So the Shapley values, so As mentioned before, in order to get a value for the contribution, we can calculate these Shapley values. And the definition of Shapley values is a weighted average marginal contribution of a feature value across all possible coalitions. And when I read this, the first one, it was quite complicated, but there are two terms in it: marginal contribution and coalitions. And I will explain both of them in the next slides in more detail. But to mention the goal. So the goal of Shapley value is to explain the difference between the actual prediction with specific feature values and the average prediction. That means to answer the question why a specific prediction was reached in comparison to the average prediction. So to see what the marginal contribution is, let's have a look at what a marginal distribution is. Imagine the players want to order food after they played, and they should indicate their preference from 1 to 10, and it should add up to 10. So player 1 said, I don't like pizza, but I like a lot sushi. And player 2 said, actually, I don't really care. Player 3 said, pizza is okay, sushi too, but I don't like burritos. And player 4 says, I like pizza, maybe sushi. So, and then we can compute the marginal distribution of pizza, burritos, and sushi. That means the overall preference independent of a single player. So the concept between marginalization is that the effect of single variables is eliminated. So it's called they are marginalized out. So here we compute the marginal distribution of pizza, burrito, and sushi independent of all players by summing up. And then you can represent it in percent, or you can compute percentages from it. And also this sums up to 100%. And if they order food, it will most likely be sushi. Okay, yeah, so marginal contribution is the contribution of a player or a feature when other effects are marginalized out. That's the marginal contribution. And then the another term was coalition. So a coalition is a set of player or features. Imagine you want to analyze how much one player contributes to the overall payout when playing in different coalitions. So this is actually what you want to know. So how much is the contribution of one feature when it's put into a coalition of other features? And the so-called grand coalition is when all players or all features perform together. That's a set of all features and or players. So here we want to we analyze the green player, and when we want to analyze the green player and how he contributes to different coalitions, we have 3 players left, and if you have 3 players, you can have 8 coalitions. So one is the set of 3 players. One is the set where no player is included. Then we have the 3 sets of where only 2 players are included, and and 3 sets, 3 coalitions where only 1 player is included. And you want to know what is the actual contribution of the green one when it's put into one of these coalitions. That sounds really nice from a game theoretic perspective, but the challenge is in machine learning model, we cannot evaluate with less than the features. So it's not that you can take out a feature and then analyze something. It could be possible when you train separate models for each number of features, but this is computationally super expensive. And also this is nothing we want to do, because then you have a lot of models and it gets really complicated. But there's a really nice alternative. So what you do is you fix all feature values which are in a coalition. So this is fixed. And then the feature values outside a coalition are randomly sampled from the data set. So they're treated as unknown. And this can be done because you are marginalizing out the effect of other features outside the coalition. So what you actually do when you want to analyze the green player and how it contributes to, for example, here such a coalition, you treat the other features as unknown. That means you randomly sample from the data set, and then it's marginalized out the effect. And I will go step by step through it, how it's computed, because I think then it's easier to understand. But first of all, I want to show you the equation, how the Shapley values are computed. And again, it's a formula, it's an equation. When you look at, it's like, okay, not so obvious, but let's go through all the elements. So given all this information and the definition of the Shapley values, so let's have a look how they can be computed for a single prediction. That means a single input sample. So first of all, this is the Shapley value for feature D. So V is the Shapley value, D is the index of a feature. Then we have here, this is the total number of features. That's the ground coalition. In our case, with the 4 players, the D would be 4. Then you have the coalition, which you analyze at the moment. This is a subset. And then here you have a sum over all coalitions without the feature D of interest. So you sum exactly what I showed you before on the plot. You sum how much the green player contribute to all the coalitions. This is the sum. Then you have 2 terms here. This is the output after feature D is added to a coalition. And this is the output before feature D is added to a coalition. So this is actually how it's analyzed. What is the contribution? And then there's actually this term here. So let's go back. First of all, so S is the coalition subset. When you have this around it, it means the size of the subset. So if you have if S has 3 players in it, that's actually 3. And this is the factorial. So this exclamation mark, that's factorial. So if you have a subset of size 3, the factorial is actually 3 times 2 times 1. If you have 4, it's 4 times 3 times 2 times 1. That's a factorial. It's I tried to wrap my mind around this kind of normalization, and I found a good intuition behind it. So this term corresponds to the fraction of times S appears in all permutations. So actually you have a lot of permutations, but intuitively, this gives the highest weight to the most informative contribution of players. So most informative is the contribution when it's either isolated, when the player plays alone, or when it's added to otherwise full coalition. So when everybody's already there and it's added. So this is most informative. So this weight is high for these 2 scenarios, and then it gets a lower weight when you have some other kind of coalition. So this is the best intuition I found, and I think it's okay. But yeah, so the equation here, this one, needs to sum the contribution of a single feature to different coalitions. So you have a sample, a single feature you want to analyze, a specific feature value, and you want to analyze different coalitions. So let's have a look how the contribution of one feature value to one coalition is actually computed. You have 4 features, X1, X2, X3, X4. The current coalition is X2 and X3, and you want to know what is the contribution of X1 to this coalition. What you do for this is step 1, you first add X1 to the coalition. So you have this S and it includes now X1. Then you randomly sample a value from X4 because it cannot be ignored. You randomly sample a value for X4 from the data set and compute the output. So this is what is here. You take the data set and you grab a value for X4. What you do then is you remove X1 from the coalition. I forgot to say, yeah, and you compute the output. This is important. This is one value you need to store. Then you remove X1 from the coalition because you want to actually know what is the contribution of X1, like this. And then you randomly sample a value for X1 from the data set and compute the output. So both of these, due to this random sampling, the effect is marginalized out. So you can compute the contribution of X1 by subtracting from the value which is the output when when X1 is added. Oh, this is actually not D, it's X1. So new slides always happens. So this is when X1 is added, and this is without X1. And to actually get this marginalizing out effect, you need to repeat the sampling for the feature values outside the coalition. And there are some, I asked my student who was dealing with it, and he told me he found a value like to repeat it 100 times. This is a default value, for example, but it depends how large the data set is and how diverse your data sets, the values are. Yeah.
Just to understand, so the function f doesn't need 4 inputs?
Can you say it again?
F doesn't need always 4 inputs, so x1 to x4. But s only has
yes.
2 to x3.
Yes.
So should it be found with s for the sample of the original x1 and then the sample to x4?
Yeah, it's so you have all the values in there. Here indicated it's just what is currently in the coalition. So it's the, yeah,
and
that's
missing in the coalition is when you sample. That's
yes, yeah,
line.
right,
Yeah.
exactly. Ah, right, that's good point. So it's always good when I make new slides to get such feedback, because this is not clear. That's good point. Yes. I mean, you have one model. It's you cannot remove just something. It's yeah. It's maybe I added additionally. Good point. Yeah.
We have to consider that because before X1 was part of the coalition, that you don't randomly sample the same value in it.
That's actually on purpose that you do it. So it's you do not influence at any point how X1 is sampled. It can be the same value actually, or a different value. Yeah. So let's come back to this to this equation. So once again, the Shapley value is the weighted average contribution of a feature value to the prediction in different coalitions. And here you have the this is actually what you do here, and then you sum over all different coalitions. And not to be confused, I know it's oftentimes misinterpreted, or what the Shapley value actually tells you. So it explains the difference between the actual prediction with specific feature values and the average prediction. So why does something else happening when I have a specific feature value in comparison to the average prediction? And it's not the difference between the actual prediction and the prediction after it was removed from model training. So this is something else. But yeah, just to be careful. And one really nice thing about the Shapley values is that they have properties, and nearly none of these interpretation tools will give you similar properties. So let me briefly go through them. So first you have efficiency. So the sum of single Shapley values equals the value of the ground coalition. So when you compute the contribution, if you put them all together, it's actually it equals to the grand coalition. So the overall payout. And then it's symmetric, also important. So the Shapley values of two feature values should be the same if they contribute equally to all coalitions. I mean, this might sound obvious, but a lot of interpretation tools will not have these properties, just to mention it here. And then the dummy property. So a feature value that does not change the predicted value has a value of 1, a Shapley value of 1. Also good. And additivity. So for predictions that arose from added predictions from individual models, the Shapley values of the individual models should also add up to the Shapley value that arise from the overall model. To give you an example, suppose you trained a random forest, which means the prediction is an average of many decision trees. And the additivity property guarantees that for a feature value, which is from which you calculate the Shapley value on the single trees individually, and then you average them, it's the same as the Shapley value for the feature value of the random forest, which is also nice. And I think these are really nice properties, and it's a very sound mathematical ground, which is also not the case for a lot of interpretation tools. And just to give you some advantages and disadvantages so that you can get an impression on if you should use it or not. So, as I said, most of the interpretation methods don't fulfill all 4 properties. And the Shapley values can take into account the whole data set or just a subset. This is useful for analysis. So here, when you look at the definition, you can compare it to the average prediction of the whole data set. But maybe it's also interesting to analyze just a subset with specific characteristics and just compare how's the contribution to this specific subset. But it also has some disadvantages. It's oftentimes misinterpreted. It also happens to me still, even if I look again and again and again. And it's only reliable for data sets with a lot of features, because there's a whole marginalizing out and there's summing of all the coalitions. It's if you have only a few features, it's not so it's not so reliable. And you need access to the data set, which is also one thing which is not always the case. And this computation is super expensive because you need to compute all the coalitions. And I remember when we did experiments, it took a while. But they're efficient implementations and mostly tailored to specific model types or architectures. I do not want to go into detail, but there's a really nice SHAP library. SHAP is the Shapley additive explanation. So Shapley values is actually the mathematical theory behind it, and the term used or the method used in explainable machine learning is SHAP. And you can find good implementations there, for example, for tree-based methods or some speeded up computations for any kind of models. Yes. Yeah. It's really nice. And it will give you really nice plots like this. Some of you might already have seen such kind of plots. So let's come back to the actual experiment for ozone value prediction. What you see here is so-called summary plot. On the left, you see here the use features as input, some of them. Right next to them is the global importance, which is the average sum of the absolute Shapley values. And so we have a lot of these samples with different feature values. Not a single anymore. You have the whole data set. But of course, the Shapley value, you always compute for one single value. And this colorful part are the Shapley values for single predictions illustrated in a B-span plot. So here what you can see, blue are, for example, absolute latitude values with a low value. And here you can see the Shapley value. And red is high feature values. But each dot is a single analyzed Shapley. Now you see why it's computationally expensive to compute it. And as a side note, this plot only shows features with more than 1% global importance. The rest were identified as not important for model prediction. So the global importance here of what you can see in the plot, the global importance of the features absolute latitude, altitude, and relative altitude and night light in 5-kilometer area are highest with a contribution of at least 10%. And the remaining features have a weaker influence on the model output. And in the last row, for example, the climatic zone can often be, it's not really, it doesn't really have an influence. And here, the left plot, to give you a few more interpretations. So when I talked before about the contribution, it always means the added value to the payout, the actual prediction in the end. And so the left plot is actually the right. I was confused right and left. So this part here reveals the contribution of features to the prediction. So let's have a look at the first row. In the first row, you can see that the absolute latitude value leads to an increased ozone value prediction. So that's why it's indicated if it has a low value or a high feature value. And so low feature values have a high contribution to the overall payout, which is the prediction. And in the same way, higher altitude and relative altitude increase the predicted ozone values. And yeah, so, and this is, as I asked or as I heard, and it's also written in the paper, this is in line with domain knowledge in the specific area. So this is one, one thing. Did you have a question?
Yeah.
Okay.
Do you have any idea about this outlier of kind of the low absolute latitude is -5%?
Yeah, that's a good question. I don't know.
It's interesting to see kind of which feature it is actually, so kind of which data point you can trace it back.
I think, yes, I don't know if it was analyzed in the paper, but in the, no, okay. It's, would be interesting, yeah. And this is actually why explainable machine learning is so cool, because then you have such insights and then you kind of have a look at your data.
Most knowledge are kind of ordered more or less in terms of the
yeah.
some are kind of those are interesting.
Exactly. This is also what we did when we had a look at the whales, when the heat map was actually indicating that it's really good, but the score of the network sets is a really bad result. So these contradictive examples are the most interesting ones. Yeah, that's true. Yeah, so I can recommend to go to, if you want to try it out, this library. It's really nice. But of course, be careful when you have correlated features. It might, it might give you misleading results. So you should check, or you need to think a little bit before also what to integrate, or do some prior feature importance analysis also. So for the rest, perfect. I'm really good in time. Okay, so for the rest, I would talk about not using expandable machine learning for analyzing what we already know, but to discover something new. And this is actually one project in Kista. And here we use explainable machine learning to understand wilderness. So the problem is there's currently no technical definition of wilderness that can be used for mapping of wilderness with machine learning. So worldwide mapping of wilderness cannot be done at the moment because there's no existing definition which is useful for it. But there are a few, like the one of the European Commission, like this one. A wilderness is composed of native habitats and species and large enough for the effective ecological functioning of natural processes. But it contains vague terms like large enough. So what is large enough? It's native. What is actually native? When is something not native? So we intend to use explainable machine learning to discover characteristics of wilderness to deepen our understanding about the land cover class so that it's useful for mapping. So in the beginning, we had the ambition that we want to find a definition for wilderness. And now we realized after working on it a little bit, it might not be we should first understand a little bit more about it. And then we might maybe come up with the definition at some point. So what we did is we have a focus on Phenoscandia for our analysis, and we developed a neural network which can distinguish between areas we can clearly assign to either wilderness or non-wilderness. So Phenoscandia is Norway, Sweden, and Finland. So this area here, and we defined a training data set with wilderness area, where we can say they're associated with wilderness characteristics, which is from the World Database on Protected Areas, short WDPA. So clearly here we would say, okay, that looks like wilderness. And then we have anthropogenic areas, which are artificial and agricultural surfaces. So clearly no wilderness. And we used Sentinel-2 data for our analysis. So here you can see some images with anthropogenic areas, and here some areas or some image patches from protected areas. And as you can already see, green and forest is not a good indicator because it appears in both. So it's not wilderness, it's not trees. What in the beginning we thought I think in our heads, or very often when we ask around, it's the first thing we think of. It's green, it's nature, something like this. But it's not that easy. So we trained a model, and our network is actually a combination of so-called UNet and convolutional neural network. So UNet is a specific type of convolutional neural network which has this encoder and decoder structure. And you can see here the input image and here the UNet. And then we use the output of the UNet, this activation map, which are usually used for the decision making, and take a closer look to it. And in order to make, so this is what we later use for the analysis. And in order to make an actual decision, we added another convolutional neural network, so this part here, and a fully connected network to have a classifier for wilderness and non-wilderness. And the whole network is optimized so that we can make good decisions on the one hand, and during the process also we derive good activation maps. Yeah.
You also need the last part for the example GradCam to make these kind of heat maps too. Because when you have these slides, I saw that you always have the structure with the getting smaller layers for like other smaller shapes.
I think
the unit you can directly make a
right. Yes. I think we never tried GradCam on this because to be honest, I have no good experience with GradCam on satellite images, because I think for GradCam, you need this typical foreground background structure or objects in an image. For the wave fluke, super good, but for a satellite image, I just don't have good experience with it. At the very last slide, I added one paper, which I think it's really, I can recommend for reading, where they go a little bit into deeper why these saliency maps, these heat maps and gradient-based methods might not work in many cases.
And is this still a pixel by pixel approach, or is it a generalization of?
No, actually not. Yeah, I can go. So this is a more detailed network. Actually not. We perform scene classification. The middle part here could be used for semantic segmentation, but this is not, we cannot collect training. I mean, we did collect training data, but at this point, we just want to point to areas where we say, this is a wide area and this is not wide area. And then we want the network to figure out what are the patterns in each of these images, what led to the decision that is a wide area or not. So we wanted to give information, but not to bias the network or not to give too many information. Also, it's really hard to have training data for semantic segmentation when such a concept is just not known yet. So we tried to find a compromise. Actually, we started with semantic segmentation, and then it was, yeah, we turned to this approach. Yeah. So here you can see this specific architecture. These actually these arrows I didn't tell before. These are so-called skip connections. So you copy what you have here to the other side. So things from the encoder are copied to the decoder. Really nice, yeah, component of the architecture. Okay, so this is our network, and what we do is, yeah, we have some anthropogenic images and we have some wilderness areas, and now we perform here classification. That's actually, I showed it before, a little bit different. We have only one output because we have two classes, and it's enough to get the prediction for one class because we assume it sums to one. So it's actually just the opposite. So we want to have the score for wilderness in this case. And as I said before, we trained with images which we can clearly assign, because this is what we can. What we can is we can say this is a wilderness area and this is not a wilderness area. We are not sure in the middle, so we want to define it a little bit more detail and understand it more. That's why it's totally fine that we have accuracy, and actually that was intended, that we have accuracy for our network which are close to 100%. So this is how we know that our network is able to distinguish between these patches. So the intention was, we do not want to have any big uncertainties in the decision process, and because uncertainty in the decision process would lead to uncertainties in the interpretation and explanation. We can go there at some point in the project, but for now, we want to rule this out. Okay, so now here, this is what we now look at. After this unit output, this has exactly the same size as the input. We have activation maps, several ones, and this is one hyperparameter we can tune. So what do we now do with these activation maps? So we had more than 19,000 training samples. And for all of these training samples, we got activation maps, and not only one, but three of them. So we had 3 filters in the final convolutional layer. So we have for each of these image, yeah, an activation map with 3 channels. And then we put the pixel-wise, we took all the pixels from these 3 activation maps in a 3-dimensional activation space. And you can already see nice pattern. That's actually what we thought when we saw it. So it's not like an exploded pillow. There's actually a structure in it. And this is, so now you might ask, okay, what to do now with it? And remember the concept of occlusion sensitivity maps. So for the occlusion sensitivity maps, we worked in the input space, but we can also perform this in the activation space. So what we do is, or what we did is, we defined a cube and we systematically went through the activation space and we set all activations in the cube to 0 and analyze how the score of the network changes for wilderness. And this is here, it actually makes sense because when you set activations to 0, this means no signal. I mean, depends on how you define your architecture, but you just cancel out the information in the network. So we covered it up. Here we set all this to 0. That means, so when you look at this middle image here, and if we set this to 0, this is actually what's happening. So all the values in these activation maps are set to 0. Okay, so then we computed, or we did this for the whole space, and then we computed. So we have this covered up, partly covered up activation maps, and then we had to look how the score will change, and this is the sensitivity. That means the change in the score for all these images. And you can already see that activations which are in this corner of the activation space are very sensitive towards non-wilderness. And here in green indicated as high sensitivity towards wilderness. So when you cover up all these activations in this area, the score for wilderness goes down. So it's a very important activation, a very important pattern for wilderness. And so this is nice, but to give you a little bit better impression about it. So this is when we feed in and test image, because this can be, so this was computed with the training data, and this is what you have then. But if you then feed a test image into the network, you get the activation, and you can just, like a lookup table, look for the sensitivities and translate it to such a sensitivity map. And so here illustrated is one image which was not used during the training process, and in green illustrated are patterns identified by the network which are sensitive towards wilderness, and in pink are regions and patterns sensitive towards non-wilderness. Like here, for example, it's green, but they're artificially created forests. So that is a reforestation area. And we also found out that, for example, water was always neutral. So there was actually no really a sign. And here you can see some agriculture areas or some agriculture fields. And such experience might help us to understand patterns and process hidden in our data in a much better way. I mean, you might think, that was obvious, but not everything what we discovered was obvious for us. So sometimes we were really surprised. For example, in the beginning, we clearly said, okay, forest is an indicator for wilderness, and it was just not the case. But we also see that this is now restricted to Scandinavia. And if you want to go to another area, you need to retrain the model or extend it. This is also clear. And this can also be, you can also have a look at different time steps. And so first, let's have a look at the bottom row here. So this is an area from 2017, and this is an area of the same area in 2020. And if you look at the satellite images, I mean, it's a little bit small here, but it was not so clear in the satellite image, but if you look at the occlusions of the activation space occlusion sensitivity, it turned out they changed a lot. So the anthropogenic area increased a lot, expanded. And here is one comparison to, or two comparison to the occlusion sensitivity maps, which I showed you in the beginning, where you covered up something in the input image. And this is not so, I mean, you can see similar patterns, but it's not so obvious. Yeah, so for example, it can be seen that most from the occlusion sensitivity maps, most of the part were neutral. So there are nearly no areas which are associated with wilderness patterns. Okay. So just to give you a very last impression, what we also did is we combined it with the Korean land cover. And so we mapped the Korean land cover information, which is given. I mean, you can download it, it's given, and you can, because you have an image, you have the Korean land cover and you have your activations here, you can actually connect it. And we had a look in which land cover classes are actually connected to these different activations. And you can also see a pattern in here. So it's with this way, we could at some point also say, okay, wilderness patterns are connected with specific land cover or more specific land cover areas, something like this. It's not, it's work in progress, but that was already nice to see that also this shows some patterns and relations. And this is my, I have 2 slides left. Because there's always a question when I give similar talks about the evaluation. And this is an open research question, but I give you some just some impression of what is already there and how people think about the evaluation of interpretations. And this is restricted, or here mainly for models aligned with existing domain knowledge. So this is not if you want to discover something new. This is when you, for example, want to increase the trust. And they're actually in this paper from which I found really nice, they mentioned 3 types of evaluation you can perform when you look at your interpretation. The first one is the application level evaluation. So here you quantify how easy an expert can explain the same decision as derived by a model application. So you let an application or a system make a prediction, and then you see an explanation, and then you see if an expert would explain it in the same way. Then there's a human level evaluation. So here present different types of interpretation, and then you let a layperson select which one is the best. I also read in the paper recently that they gave explanations to people, and then these laypersons, they measured if this interpretation helped to make better prediction or to produce better labels, and it didn't work. So that was also interesting finding. So your interpretation should help to understand the decision process better, and obviously in this study it was not the case. And then there's a function level evaluation. So how easy is the interpretation based on known preferences? For example, if you feel better with a decision tree which is very small, then your model should not be a complex random forest. This is also something what can be evaluated from a interpretable model perspective. So to conclude, what are my takeaways for you? Explainable machine learning is not new. So feature importance has been there, computing the feature importance has been there for many, many years, especially in the context of random forests and decision trees. It just is sometimes a hype, or it just got more advanced because now neural networks are there and they're so complex that we cannot understand them. And so a lot of new methods were developed. That's why it seems new. Explainable machine learning offers a lot of methods which need to be chosen carefully based on your analysis score. This is what I mean when really think about if you want to analyze sensitivity or the contribution. It's connected to uncertainty quantification. Remember the example with the whales where we compared the detection rate and the kind of heat map. And it goes beyond explaining models which are aligned with our given knowledge. So you can also use it to discover new things, which I think is really interesting. But you need domain experts. Otherwise, it's not an explanation, but only an interpretation. And here is some further literature. So this is one really nice book. It's online available for free. It's also work in progress, but it's really nice. I also used it for the preparation of the slides. Then heatmapping.org is a quite old page, but here you find a collection of tutorials. And these are the people who invented the layer-wise relevance propagation. I did not mention here, but it's also cool. And this is actually the paper with the sanity checks for the saliency map. So I can recommend to read it. And with this, I thank you for your attention. I hope you learned something and it was interesting for you. Thanks a lot.